In 2023, Boston Dynamics released internal test footage of their Atlas robot completing a full obstacle course, jumping, vaulting, and sprinting at a sustained pace that would beat roughly 60% of adult humans in a 100-meter dash. The company almost didn't release it. Engineers debated internally whether showing the public exactly what Atlas could do would trigger the kind of panic that slows down research funding. They released it anyway. The clip hit 50 million views in 4 days. And here is the part that most people scrolling past that video completely missed. The robot wasn't moving fast because it was powerful. It was moving fast because it had finally learned how to fall correctly. That single insight, that speed comes from controlled instability, not brute strength, is the key to understanding everything Boston Dynamics has built over the last 30 years. The stakes here are not abstract. They are arriving on a specific schedule, and they involve your job, your physical safety, and the economics of industries that together employ roughly 3.5 million people in the United States alone. Manufacturing, construction, warehouse logistics, military support, emergency response. These are the sectors where a robot that can move through unstructured, unpredictable terrain at human speed doesn't just improve efficiency. It replaces a specific category of human labor entirely. Amazon already operates over 750,000 robots in its fulfillment centers, but almost all of them work in flat, structured environments built around the robot's limitations. The moment a robot can navigate a construction site, a collapsed building, or an irregular factory floor at the speed a human worker does, the economic calculation changes overnight. Boston Dynamics' own projections, shared with investors in 2024, described a commercial robotics market reaching $260 billion by 2030. That number assumes their hardware hits its mobility targets. Current testing suggests it already has. The second implication is less discussed, but more unsettling. When a machine can outrun a human, the entire doctrine of physical human oversight, the assumption that a person can always intervene, redirect, or shut down a robot by simply being faster, collapses. That assumption has been quietly embedded in every safety framework for autonomous systems written before 2020. To understand how Boston Dynamics got here, you need to go back to a DARPA contract in 1992. Marc Raibert, a robotics professor at MIT, had spent years studying one deceptively simple problem. How does a one-legged hopping machine stay upright? Not a wheeled robot, not a tracked vehicle, a machine that balances on a single point and moves the way biological creatures actually move. Raibert's core insight was that legged locomotion is not a balance problem. It is a falling problem. Every step a human or animal takes is a controlled fall forward. You lean slightly past your center of gravity, and your leg catches you at the last possible moment. You are never fully stable. You are perpetually recovering. This sounds obvious once you hear it, but it inverted 30 years of robotics thinking, which had been trying to build machines that were statically stable, meaning they could stop at any point and not fall over. Raibert's robots were dynamically stable, which means they would fall over the instant they stopped moving, exactly like a bicycle. That's the analogy. A bicycle is impossible to balance at zero speed, but effortless at 20 miles per hour. Raibert's lab became Boston Dynamics in 1992, and they took that bicycle logic and began applying it to machines with 4 legs, then 2. Every subsequent generation of their robots is built on this foundation. You cannot understand what Atlas does in 2026 without understanding that 1992 hopping machine. The first major revelation in Atlas's development is what engineers call proprioception, and it is the reason most people fundamentally misread how this robot works. When you watch Atlas navigate a beam or land a jump, your instinct is to think about motors, actuators, maybe sensors. But the real architecture is informational. Atlas has an inertial measurement unit, essentially an extremely precise version of the balance organ in your inner ear, that updates its understanding of its own body position 1,000 times per second. By comparison, the human vestibular system processes orientation signals at roughly 100 to 200 updates per second. Atlas is monitoring its own falling trajectory 5 times faster than your brain monitors yours. What this allows is something extraordinary. The robot doesn't plan movements the way early robots did, by calculating the optimal path before taking a step. It plans them continuously, mid-motion, adjusting the next footfall based on what its sensors detected 0.001 seconds ago. The result looks fluid because it actually is fluid. Engineers call this model predictive control. The robot is constantly generating a short-term forecast of its own physics, roughly 0.3 seconds into the future, and optimizing against that forecast in real time. Here is the concrete implication. This is why Atlas can be shoved, pushed, or placed on uneven terrain and recover. It's not reacting to the shove after it happens. It's updating its model during the shove, calculating the new fall trajectory, and redirecting before it completes. That capacity, real-time physical self-modeling, is the breakthrough that separates Atlas from every wheeled or tracked robot that came before it. And it directly enables what the company did next. The second revelation is harder to accept because it challenges something most people believe about the fundamental nature of robotics. For decades, the assumption in the field was that a robot capable of complex physical movement would require massive external computation. A server farm essentially puppeteering the machine over a high-speed connection, doing all the heavy calculating remotely. Atlas runs almost entirely on onboard computation. The current generation carries processing hardware roughly equivalent to a high-end laptop, and it performs every movement decision locally, in real time, without phoning home to a data center. This is not just an engineering convenience. It is a philosophical shift. It means the intelligence, the part that decides how the body moves, is genuinely embodied. It lives inside the machine. Boston Dynamics achieved this by radically shrinking the problem. Instead of teaching Atlas to reason about the entire world, they built layered controllers. One that handles low-level joint torque, one that handles balance, one that handles task execution, and one that handles high-level goal planning. Each layer only communicates with the ones adjacent to it. Think of it like the chain of command in a military operation. The general doesn't call the individual soldier. He calls the lieutenant. The lieutenant calls the sergeant. The sergeant issues the ground-level order. This hierarchy reduces computational load at every step. The result is a machine that weighs roughly 89 kilograms, stands 1.5 meters tall, and can execute a running backflip, with both feet leaving the ground simultaneously, landing within a 15-centimeter target zone, consistently, without a single external instruction during the execution of the movement. That statistic alone should force you to reconsider what the word robot means. The mechanism that actually makes Atlas run fast is called whole-body control, and it is the piece of the engineering that most explanations skip because it sounds technical. But it is essential, and you can understand it in plain terms. When a human sprints, your body doesn't move your legs independently from your arms and torso. Everything coordinates. Your arm swing counteracts the rotational momentum of your legs. Your core muscles stiffen and release in precise timing with your footsteps to transfer energy upward and forward. Your ankle, knee, and hip joints each contribute a different phase of the stride's power cycle. Remove any one of those and your speed drops by 20 to 30%. Early robots moved only one joint at a time in a predefined sequence. Atlas uses whole-body control, meaning every actuated joint, all 28 of them, is included in a single optimization calculation on every control cycle. The system treats the entire body as one physical object, not a collection of connected parts. This is the analogy that makes it click. Imagine choreographing a 28-person dance routine where every dancer must adjust in real time to what every other dancer is doing simultaneously 500 times per second. That is what Atlas's controller is doing, expressed in the physics of a single body. The counterintuitive result is that running is actually more energy efficient for Atlas than walking slowly, for the same reason it is for humans. At higher speeds, the elastic energy stored in the joints during impact can be recycled into forward propulsion. The robot bounces forward the way a well-pressured basketball bounces off a hardwood floor. The complications are real, and they deserve direct treatment. The first is fragility under extreme conditions. Atlas performs reliably in structured test environments and controlled outdoor settings. What it cannot, yet do consistently, is operate in conditions humans navigate every day: rain-saturated ground, unpredictable crowd contact, extreme cold that degrades hydraulic performance, or construction debris that the onboard sensors cannot identify quickly enough. In field trials conducted with FEMA in 2024, Atlas completed roughly 78% of assigned search tasks successfully in simulated disaster environments. That sounds impressive until you consider that the 22% failure rate in a real disaster represents people who were not reached. The second complication is legal and ethical, and it is moving faster than the engineering. There is no current federal framework in the United States governing the deployment of autonomous mobile robots in public spaces. Boston Dynamics operates under self-imposed guidelines and state-level patchwork regulations that vary enormously. In 2020, the ACLU formally objected to the NYPD's lease of Spot, Boston Dynamics' four-legged robot, citing concerns about surveillance and the chilling effect of robotic police presence in public protests. The NYPD ended the program under public pressure. That tension has not been resolved. It has simply gone quieter while the technology has gotten faster. A machine that can now outrun most humans in a public space, and that carries no binding legal constraints on its behavior, is a policy problem that no city or federal agency has yet seriously addressed. This technology will enter your professional life before most people expect it to. If you work in logistics, warehousing, or manufacturing, the timeline is not speculative, it is contractual. Hyundai, which acquired Boston Dynamics in 2021 for $1.1 billion, has explicitly committed to integrating Atlas-class robots into its automobile manufacturing facilities by 2028. That is not a research goal. It is a capital deployment plan. If you work in construction, emergency services, or any role that involves physical navigation of complex, unstructured environments, you are looking at a 5 to 8 year window before robotic systems are cost competitive with human labor in your sector. The actionable thing to understand is this: the jobs that survive longest are not the jobs that require physical strength. Robots have had that for decades. The jobs that survive are the ones requiring real-time social and contextual judgment. An emergency responder who can calm a panicking person while simultaneously assessing structural damage. A construction foreman who can read the mood of a crew and adjust the work plan accordingly. The economic threat is specifically to physical roles that do not require emotional intelligence. Watch the insurance and bonding industries carefully over the next 3 years, when commercial insurers begin writing liability policies for autonomous mobile robots in industrial settings. That is the signal that deployment has become mainstream. Zoom out and consider what 30 years of this work actually means. Boston Dynamics began with a one-legged hopping machine in a university lab, trying to solve the physics of falling. They now operate a robot that runs, jumps, flips, and